welcome back. So I'm going to chair the Blitz talks because apparently people think I'm mean enough to do it. That's supposed to mean, but so the way this works, these are 8 minutes, absolutely no more than 8 minutes. There will be an alert of sorts after 8 minutes, and then the speaker pretty much has to stop mid-sentence. There will then be 1 minute for questions, and I will cut off questions after a minute because the next speaker has 5 minutes to get up and prepare himself. So we need to give time for that. I will be a little bit more generous with that, but not too generous. So with that in mind, let's start with go.
Okay, hi, thank you. Thanks for letting me be the first one, so there's no better talk before me. So I'm going to tell you today a bit about stuff that's going into my thesis. Just because I have 8 minutes, I'm basically going to skip over all the technicalities. If you want to ask me about the technicalities, we can talk about it later, I suppose. But essentially what I've done is I've just gone and taken like classical geometric quantization and then redone everything in a stratified setting. So let's just first talk about what you do with the sort of classical way. So what do you need to do quantization? We need 3 things. You need a symplectic manifold, something called a polarization. It's just a Lagrangian subbundle. It satisfies some properties. And then you also need a prequantum line bundle. Okay? And then once you have those 3 things, you can go ahead and try and define quantization however you want. And one way you could do it, for instance, is you could take what are called the polarized sections. So you just take all the global sections of your line bundle, which vanish when you pair them with the sections of the polarization. Okay, so that all makes sense. Now, of course, we want to make it all equivariant because I'm going to be doing stratified stuff later, and obviously reduction is where you get stratified things. So, so first, let's just let G be a connected Lie group, and I'm going to demand that it act properly on M. Okay. So once you have that, I'm going to define this symbol mu going to G star. That's the dual of the Lie algebra. Okay. So this is just going to mean 3 things. One, I have a momentum map. I'm going to demand that the polarization is G invariant and that there's a lift of the G action to the line bundle and has to intertwine the momentum map and the connection. Okay, so now once we have all this, we can start doing our reduction. And of course, we have Eugene and Ryer. I don't know if they're here, maybe. Yep, so if you just take the level set at 0 and then you quotient by G, then you get something called a stratified symplectic space. Okay, so it's just a singular symplectic thing. And of course, the question is, what about P and L, the polarization and the line bundle? Can I also drag them down? What does it mean to drag them down, like to be stratified? And so my answer to that is basically just redo differential geometry, in particular vector bundle theory, because those 2 things are vector bundles, in the stratified world. And I have a paper where I did that already. So now using that, we can move on to the stratified spaces. So just roughly speaking, what are these things? They're 3 bits of data. One, you have a topological space. Of course, that satisfies a whole bunch of stuff, but whatever. Then you have a partition into smooth manifolds. So I've shown here my space is the square. The partition is into these edges and faces and the vertices. Okay, those are all smooth manifolds. And then you need some notion of smooth functions, like a sub-Cartesian structure, for instance. Okay, in this case, it would just be restriction of smooth functions on the plane to the square. So that would make this into a stratified space. And of course, there's lots of stuff you can say about these things. Okay, so now how do we do differential geometry on one of these things? Well, the rough idea is that you just do some stratum by stratum construction. Okay, each one of those is a smooth manifold, so I can just do my normal differential geometry. And then after you have that, you just put some global structure on the smooth functions. Okay, that kind of ties it all together. So the classic example, and it's less technical than my other definition, so I can write it down, is the a symplectic stratified space that I mentioned before. Right, so what is that? On each stratum, you have a symplectic form. Makes total sense to ask for that. And then you also have a Poisson structure on the smooth functions. That also makes sense to do. And then the compatibility is just going to be the inclusion of any stratum is Poisson. Okay, so now using a similar idea, but it can get a little more technical, we can stratify everything else, right? So I can go from polarization to stratified polarization. I can go from prequantum line bundle to stratified prequantum line bundle, which again, over each stratum, you already know what that is because those are just normal manifolds. And then there needs to be some compatibility conditions. With the polarization involves something with the Poisson bracket, and then with the prequantum line bundle, well, actually you don't have to do too much with the prequantum line bundle. You can make sense of everything. Okay, all right, so now that we have all that, we can now start doing our quantization, I guess. So we can now have stratified data for quantization, where you have a stratified symplectic manifold, a stratified polarization. You'll notice I put this little sigma here. This means the stratified tangent bundle. That's not exactly the same as a tangent bundle, but similar to that. And also a stratified prequantum line bundle, okay? And then now everything works exactly the same as it did in the smooth case, so now you can just define quantization in the same way as before. Or you can do the cohomological wave functions. If you develop index theory for these things, you could do something like the index of some operator. I don't know if that would work out, but you could try, I guess. Nothing's stopping you. Okay, so now that you have that, we now have the theorem from my thesis, which is in progress. So if we have some G equivariant quantization data, satisfying a whole bunch of assumptions that I'm not writing down, then both the polarization and the line bundle, they both descend to a stratified polarization and a stratified prequantum line bundle on the quotient. And finally, pretty much by construction, you get a canonical map that goes from the, well, so these are sections of a line bundle. Everything has G action, so I can demand for the G invariant ones. And then pretty much just by how everything is constructed, you get a map to the, I guess, stratified quantization down below. Okay? Now, I don't know in general if this map is surjective or injective or anything. Of course, this extends the theory for where everything actually works out and everything's smooth. So obviously, those cases, it should be the same. But yeah, so that's something I'm still working on right now. But yeah, okay, and that's all I have. So thank you.
Do you have any examples of what sort of objects you get for this Q of M naught, et cetera? Like, do you get things that look like they should be the quantization of the thing that you want?
Yeah, honestly, the only ones I've actually like really worked out were, because I was hoping I would get something new, but I didn't, was toric manifolds. But yeah, it just gives you the same answer as before. Yeah.
Which is good news.
Yeah, which is good news, yeah. Hello.
Have you ever heard of
Stratifold? No, I've not heard of a stratifold.
There's a book by Craig.
Book by who?
Craig. Yes, Craig.
Ah, okay. I'll have to ask about that later.
Oftentimes the polarizations are not
Right.
Do you have anything to say about that case?
Well, so the kind of the only thing, well, yeah, what you need is just for your polarization to have like a nice intersection with the complexification, I guess this is stratified, of the level set. And then I think in that case, it should also work out as well. Yeah, as long as it intersects nicely.
Polarization is real or complex?
It could be anything. It could be real, complex, or mixed.
But only system which has a geometric quantization is like repolarization is a harmonic oscillator. There's a system that have not. So how do you do that? How do you generalize? The only system which has a geometric quantization is polarization, which is not invariant actually, which move. And this quantization is made by the theorem, which is a theorem. It's just a harmonic oscillator. So
Well, yes, I just,
there is no other system I know that can be quantized by just quantization.
yeah, so this is more,
Polarization, it's good polarization.
yeah, this is just like a abstract nonsense. As long as you have a complex involutive Lagrangian subbundle, all this machinery goes through. But yeah.
All right, that's it.
Okay.
Whoever's next. Touch that.
Sorry.
Just, this thing is really annoying. It keeps there. So just give it a couple minutes to breathe.
How do I move backwards? How do I move backwards?
How do you move backwards?
Do I press this?
Maybe it's safe.
It's not working here either. Okay. Okay. Do I get a pointer?
It's where you're pointing it.
So he just tap on the screen again, and then he releases.
Okay. So
Okay.
starting a bit early, but that's okay. So, go.
Okay. It's a great pleasure of mine to be speaking at this conference. Maybe I'll start with a fun fact that I learned about Yael, and it's that she likes to use her math notebooks from right to left, and I use my math notebooks from left to right. And for me, this is a good example of how you shouldn't expect there to be a preferred choice of orientation, an oriented manifold. So, which comes to bases, and so this is basically an idea for quantization, is to replace points on a symplectic manifold by representations or oscillators, and the representation I have in mind is the representation of the tangent vectors at a point on the germ of smooth functions at that point. So the setup you start with is a real symplectic vector space, and secretly I'm identifying it with the tangent space at a point. And so the first step is to encode the commutation relation QP minus PQ is I H bar into the Heisenberg-Lie algebra. So you add IR to V and you encode the relation into using the symplectic form. And the second step is to view the PBW isomorphisms from, I'm missing a tensor C on both sides, but on the universal enveloping algebra of the Lie algebra with the symmetric algebra of the Lie algebra. And these, I will view them as frames. And what's interesting is that because of the particular relations of this Lie algebra, maybe you have NEs and NFs. If you take linear combinations of the E's by themselves, it won't change the isomorphism. And if you change the linear combination of the F's by themselves, it won't change the isomorphism. So these isomorphisms are parameterized by complex Lagrangian splittings of the complexification. And one of the things I did was to show that for every complex Lagrangian splitting, we can construct representations of the commutation relations. And we can recover the classical ones like the Schrödinger and the Bach-Bargmann, but there's more. And what I get from this idea is that in order to quantize, we need to choose a splitting or a frame or an operator ordering rule at every point. So the question is, what is the topology of the space of frames? If you have a transverse pair, then you can contract the space of everything transverse to one into a point. So it's actually the topology of the complex Lagrangian Grassmannian. And this is known, but if we're thinking of this problem from the point of quantization, you start with real valued Hamiltonian functions. So you want to look at the topology of its the real orbits, the real symplectic orbits. So there's two basis theorems that I'm trying to interpret, and one of them is that for every complex Lagrangian subspace, there's a Darboux basis, and you have n e's and n f's, but you can partition them into n zeros, n plus, n minuses, and then you can adapt them to this choice of gamma. And for every real subspace, you can also choose a Darboux base of a similar form, and you can adapt this so that this basis and its symplectic complement are well represented by this basis. And because of this theorem, these two theorems, we can label the SPV omega orbits of the complex Lagrangian Grassmannian and the ordinary Grassmannian by these partitions of n. So this is the strata of the orbits in the complex Lagrangian Grassmannian, and so these cones are, if I want to take what are the orbits in the closure of this orbit, it's everything that's in this cone, and it's the same for any choice. So there's a horizontal symmetry in this diagram, and that is if you take the complex conjugation identifies two different orbits. And because of this stratification, you can identify this with the real Lagrangian Grassmannian, and that's the only compact component. And this happens in more generally for complex flag manifolds, and you can permute particular choices of base points by this group. If you replace the 4 by 2, it's the wild group of the symplectic group. So there's a group that's acting nicely on these base points. I've written the orbits of the real Grassmannians in the same way. So for R8, there's 9 of them. This one and this one are the points. And if you work with the indices, then the symplectic subspaces are the ones on this edge. The isotropic subspaces are elements of Grassmannians on this edge. And the co-isotropic ones are the ones on that edge. There's a horizontal symmetry again. If you take symplectic complements, you're going to identify the orbits on either side of the axis. And in this case, the incidence relations is that if you take the closure of this one, you'll get everything on the right. So this makes that everything on the isotropic and the co-isotropic Grassmannians are compact, and all the others are not. So this is an example for R2. The complex Lagrangian Grassmannian in this case is just CP1, and the orbits are SL2R orbits. And you can see that there's a homotopy equivalence between these two orbits, and that was something that I observed. But so what I'm trying to work on now is something more refined than just homotopy equivalence. So that if you choose a compatible complex structure, you realize these orbits as vector bundles over a compact space. And that compact space is diffeomorphic to this homogeneous space. That's the first step of getting rid of the non-compact parts. And then once you do that, then you can reduce every subspace, and then you get a map of this compact space as a fibration over an isotropic Grassmannian, isotropic Grassmannian, and the fibers are diffeomorphic to complex Grassmannian. And so what I'm trying to do is I can try to use the Leray-Hurst theorem or some spectral sequences to compute the integral cohomology. And yeah, that's it.
Oh, yeah.
How will it be? So, will this be relevant for what you presented at the beginning? The peers, the point, is this like the instructions for point ways?
Right. So I guess if this works, then one of the things that I could produce is maybe quantizations that are topologically inequivalent. Because of your choice of polarization, can have some topology to it.
And does, in this context, is this essential that the polarization has some negative parts?
Yes, some polarization at some point has to be negative, yeah.
Maybe one more question. Does involutivity at all play a role in your story?
I haven't thought about that yet, yeah.
Another round of applause.
Thank you.
Okay, I want to share a fun little observation regarding the classical topic of computing the equivalent cohomology via the Chang-Shelbrett method. So for this talk, T is going to be a compact torus, X some reasonable compact T space, for instance, a closed T manifold. And let me, in a Blitz fashion, remind you of what the setup is. So probably you all know this, but we're going to first, over the rational coefficients, assume that the equivalent cohomology is free. And then two nice things happen. So first, the equivalent cohomology of the space injects into the fixed point equivalent cohomology by the Borel localization theorem. And then secondly, we actually know what the image is by the Chang-Shelbrett lemma, telling you that said image is given by the intersection over the fixed point cohomologies of all the codimension 1 subtori. So you only have to know what the codimension 1 subtori do, and then you can compute this image. In particular, the whole equivalent cohomology, if you put two facts together, is encoded in the one skeleton of the action, which is nice because this is usually a much easier space than the whole thing, right? Okay. Prime application for this is the famous GKM setting, which I'm going to sort of focus on for this talk. So let me briefly remind you of what that is, although probably many of you know. The GKM case is when the one skeleton is encoded in a graph where the vertices correspond to the fixed points. So we have, in particular, discrete fixed point sets. Then you have a set of edges. Every edge corresponds to a two-sphere connecting two fixed points, right? And the two spheres get rotated by the torus action, so the orbits are one-dimensional. And the way in which this happens is encoded in some label of the edge, which I am going to take in, well, it's represented by a weight. And we see that as an element of H2 of the classifying space cohomology. Okay, then if you take Chang-Shelbrett and let it loose onto this setup, then you get the nice formula that Goreski, Kottwitz, and McPherson found of the graph cohomology, where, so this is my notation for the graph cohomology, whoopsie. In particular, I'm going to remember sort of the coefficient ring in the T downstairs here. And what this is you take a polynomial at every vertex, and then you have some congruence conditions for every edge connecting two vertices. You say that the polynomials are equivalent modulo the label of the weight, the label of the edge. Okay, now as my title suggested, I'm going to be interested in the integral case. So up until now, everything was rational. That's the classical setup. But one can do integral. And so people have looked into this a lot. So there's a work by Franz and Puppe, who really have a very good understanding of this, and I cannot do them justice in this short time. But basically, if we take what they know, then you get, and apply to the GKM case, then you get that your nice GKM formula holds with integral coefficients under some additional requirements that you need to pose. Namely, in the GKM case, this simplifies to having that any two adjacent weights of it, like weights of adjacent edges, are coprime, meaning that there is no common integral divisor of the two. Okay, so working in this with these kind of objects for too long, I became really annoyed at this condition. And also the fact that you have such a nice formula, but then as soon as two weights are like share an integral factor, you cannot do it anymore. That cannot really be the state. So what I tried was, I would try to understand this condition better and as good as possible get rid of it and see what I can do without it, right? Now, when digging into this, which is all rather fresh, I suppose for me, what I found was the following integral version of the Chang-Shelbert theorem, which I found in the text of Anderson and Fulton. It's not really a new theorem, so that's why I put the name in brackets. It's really the proof. If you go through the classical proof and be careful about integral stuff, then that's what you get out of it. And what that is you can basically replace all q's by z's if additionally you are willing to not only intersect about the codimension, whoopsie, what was that? No. If you're not only intersecting about the codimension 1 tori, but also over the maximal p tori, where the maximal p torus is the discrete group of all elements of order p. Okay? So you see that in fact, as soon as these maximal p tori give you a non-trivial contribution in this intersection, your classical GKM formula will be false, right? Because the classical GKM formula would just intersect over the codimension 1 subtori. Now, this is initially a problem, but in fact, so then I guess the main theorem in this context is the following, that the equivariant cohomology is still encoded in the one skeleton if, well, the integral equivariant cohomology is free over the classifying space cohomology. That condition we did expect. And then an additional technical condition comes up, namely I want that the fixed point cohomologies of all these finite tori, Tn being the finite n torus, should be torsion-free. Now, at first glance, that's a little bit random, but I guess in the context of this conference, it's nice because it in particular holds for Hamiltonian actions. So I get this technical condition for free. Let me very briefly sketch what the idea is, how this is encoded, because the classical Chang-Shelbert sequence is not exact necessarily. But what you do is, well, of course, first you apply Chang-Shelbert, giving you that the equivariant cohomology is encoded in the one skeleton, as well as these fixed point sets of the maximal p tori. Okay, so those are a problem. We want to understand these XTP, because they are a priori higher dimensional things we don't know, right? But what we do is we just consider the quotient action on these fixed point sets of the p tori. And our technical conditions are designed to ensure that we can apply Chang-Shelbert again. And then this goes on. So then we understand the XTP in terms of their one skeleton and some higher order XTP. But if we keep iterating this, in the end, we just reduce everything back to things that is contained in the one skeleton. Okay, how much time do I have left? Okay. Let me just very briefly point out last application for the GKM setting. So you do indeed get a GKM kind of formula. So if M is a Hamiltonian GKM, gamma is its GKM graph, then you have a description of the equivariant cohomology in terms of the graph. I added a hat to the graph cohomology there because it's not the usual graph cohomology, but you need to modify it a little bit. Namely, you need to follow this inductive procedure over there on top, which basically looks like this. You look at the subring induced by the classifying space cohomology of this quotient group T mod Tn, which is subring of the classifying space cohomology. You look at the subgraph containing all vertices and all edges whose label already lives in that subring. And then you iteratively define these objects. So notice that the case we're interested in is the case n equal to 1. So then T mod T1 is just T and gamma 1 is gamma. And you define this as the usual graph cohomology and intersect with all the h hats where you have added one prime factor, which you have hopefully already computed, and extend the coefficients accordingly. And then you're done.
Questions?
What is your prime example where you have those non-trivial contributions?
Well, I mean, it comes up all the time. So I guess if I just take a non-effective thing, it already comes up, right? So the classical GKM formula is false here. You can, of course, make this more interesting. I guess now this is not effective, but one can make it effective. Take some non-trivial bundle, maybe keep the 3x. Then I can, I don't know, twist this by adding one of this. I have like y plus 4x, and here the difference of the two. I have an interesting example of a CP2 bundle over CP1, which the standard GKM formula doesn't solve. But if this formula would then tell me to first compute this thing here in this subring, extend the coefficients, and then intersect the usual graph cohomology with it. So you get a description of this.
All right, another applause.
That's the one. Now we just need to figure out how to use this. So this I should put on myself, or?
Yeah.
Put it in my pocket. So this is back and forward. Okay, that works. And can you hear me, or? So you want me to start, or? 55 plus 8, how much is this? 3, okay. So I'll be talking about symplectic non-Hamiltonian circle actions that work as a part of my master's thesis under the supervision of Yael. So I don't have a funny joke like Hyunmoon, so just happy birthday. So the setup is we have an S1 action, it's effective, it's symplectic, the manifold is compact, it's connected, and in dimension 4. So as I think 3 different talkers said today, Yael's classified these spaces in the Hamiltonian setting by decorated graphs. So simple example would be take the sphere times the sphere, rotate both of them in different speeds, and you get this graph, right? And when you scan the level sets of the graph, you can read the non-free, that data on the non-free orbits, right? So yeah, that covers the classification in the Hamiltonian case. And what I want to talk about is what to do in the non-Hamiltonian case. So to put that in a bit of more context, in dimension 4, Yael work is on Hamiltonian S1 actions. There's also the Zan's work, which specifically in dimension 4 classifies as T2 actions on Hamiltonian T2 actions on 4 manifolds. There's Pelayo's work, which is based on joint work with Dusmat from 2010. It's worked out the case of non-Hamiltonian T2 actions. And the missing case is what I'm interested in. So this is non-Hamiltonian S1 actions. So to be more precise, the problem is classify symplectic non-Hamiltonian S1 actions. We're going to assume that there are 4-dimensional compact connected manifolds. And this is obviously up to equivariant symplectomorphism. So how do you give a classification theorem of this kind? We need to define the invariants, right, and show that there are a complete set of invariant and that we can actually construct spaces that attain the values of the invariants. So in our work, we solve this problem, but we do make an assumption on the topology of the manifold, which will actually it comes up in 3 different places in the paper, which was a bit surprising. So yeah, so again, the setting is an S1 action, non-Hamiltonian, and X is the generating vector field. So let's make one definition at least. So the group of periods of iota x omega, this is a 1 form, which is closed as we know, is all the values of the integrals over the manifold. So if it's an Hamiltonian action, this is just 0. In our case, it's going to be non-zero. And there are 2 possibilities. Either it's discrete or non-discrete. If it's discrete, then you can define a map to R mod P, which will be a circle. If it's not discrete, you can still define it, but R mod P will not be a circle, and it's kind of not useful. So to put this in a lemma, specifically, when B1, the first Betti number of the quotient space is 1, apparently you can always define a circle-value Hamiltonian. So P is always discrete. You always have the circle-value Hamiltonian, which is unique up to the translation. And the fibers are connected, which is very nice. It makes like the choice of R mod P a unique choice, a natural choice in some sense. And so some example, take the torus, rotate it at speed k, take the sphere, rotate it at speed L. So then you get this Hamiltonian here, where p is one of the coordinates of the torus, but p is only defined up to mod z. So this is well defined up to mod kz. So here the group of periods is kz. Okay, so one corollary which is pretty much known is that the induced map on the quotient space of the Hamiltonian gives a topological oriented surface bundle over the circle, which is the image. And every fiber has the same number of non-free orbits with the same representations. This is because McDuff showed that there are no fixed points in this case, so when you flow upwards, like the non-free data cannot change. So that's the same example, but this time just rotate the torus, so it will be easier. You take the quotient, so now this is the quotient map. You get the induced map. The induced map is just the projection on the circle, right? And so the level sets look like spheres in this case. Here the direction is free, so there are no special points or anything. But in other cases, you might have like finitely many special points in each fiber, which go up around the circle. So yeah. So now let's define 5 invariants for our spaces. The first one is the group of periods. This is invariant under covariant symplectomorphisms. Second one is the genus of the reduced spaces. Like in the case of complexity 1 spaces, this does not change when you change the level sets. Next is the Dussel-Mann-Techman measure. So this is actually a constant. When you go around around the level sets, it cannot change because there are no fixed points. So the derivative is constant, but you go around the circle, so it has to be constant. There's the final list of representations of the non-free orbits. And lastly, there's like a topological invariant, which I call the monodromy invariant, which is basically the data on the gluing map that constructs this surface bundle. So the quotient map, the quotient space is a 3-dimensional manifold over the circle. You can always construct these bundles by some gluing map. But this gluing map also holds information on the topology of the non-free orbits. So we said there are like finitely many non-free orbits in each level set. So when you go upwards, they might braid each other. So this is like an illustration. You start in the level set, you go upwards, they might make braids and stuff, but then they have to come back to orbits of the same type. So here it's color, but it's basically the representation. Yeah, so example of some calculations, if you take this space again, then the reduced spaces of genus 0, we saw this, these are spheres. Group of periods is Z in this case, you have the area of the reduced space, there are no non-free orbits, and the topology here is trivial. It's just a trivial bundle with no non-free orbits that does wonky stuff. You can take, for instance, the Kodaira-Tharston manifold that meets an S1 action, which is symplectic, which is generated by a circle-wide Hamiltonian, and there you're going to get a non-trivial monodromy invariant, which is precisely like the gluing map that you use to construct the Kodaira-Tharston manifold. Yeah, so the main theorems are basically there exists a space for every valid choice of combination. You can construct this by taking proper Hamiltonian S1 manifolds and just gluing them when you choose the gluing map appropriately to get the monodromy invariant that you want. Here, the only constraint you have is some combinatorial constraint on the non-free orbit, so that the Dussel-Mann-Techman theorem will actually give you derivative 0. So you have one combinatorial constraint. And the next theorem is that if two spaces have the same invariance, then they are covariant symplectomorphic. And this also only works when the first Betti number of the quotient space is 1. When it's not, you can construct counterexamples for this specific set of invariants. To prove this, you basically apply tools from Yael and Su's classification of complexity 1 spaces to this map. And yeah, lastly, when B1 is larger than 1, then first of all, there might not be a circle-wide Hamiltonian. But even if you assume that there's a circle-wide Hamiltonian, then you can define the invariants, and they sort of like tell you whenever two spaces have equivalent quotients in the sense of feed diffeomorphism, if you know this notion. And you can also construct the spaces, but it does not give you a complete set of invariants. You might have different fibrations over the same quotient, and you might also have the same fibration but different symplectic forms. I think this is it. So I'll just comment on the invariants that if you know complexity 1 spaces, then maybe the first 4 invariants make sense except for the first one, which is new, but the fourth I think is the most surprising one, because it's like an equivalent of the painting invariant, but it's in dimension 4, which usually sees no topology in complexity 1 spaces. So here you have like non-trivial topology already in dimension 4, which is, I guess, a bit surprising. And this is it. And thank you.
Questions?
higher dimension. There are a couple of thoughts. The assumption on the Betty number becomes a bit more annoying. I mean, it's like I can't solve almost any case. I can discuss this in more details, but you do get like some kind of the same invariance as in complexity one spaces, but in higher dimensions, like a complicated painting that leaves not. It's not a map to the surface anymore. It has to be a map that actually remembers like what bundle you have over the image. So it's a bit more complicated. Yeah.
So it's like a sort of souped up thing. It's like a more complicated.
Yes.